Alright, so let's start using our mathematical knowledge on forces and use our force idea. So the first thing we're going to do is we're going to talk about things in what we're going to call a free body diagram. And a free body diagram is a way of representing the forces on an object. The object's going to be a free body. And so we'll sometimes do it as a point or a box, depending on what we need to do with it. And we'll label the forces that act on the body and label their direction, so that we can, force 1, force 2, we can look at all the vector quantities that go into the stability or instability of the object. And so the free body diagram, we draw a kind of schematic picture, small little picture that we need to work from. So one of the first things we're going to need to look at is, let's look at a surface of interaction, so a table, and I'm just going to place an object on the table. And I want to look at the motion of the object. So in my free body diagram, I can put my object over here. Now we know gravity is pulling down on the object. And so I can say force of gravity, and from our previous conversation, that's the mass times the acceleration due to gravity. And we get that relationship. But if we look a little deeper, this object isn't moving. Newton's second law says the sum of all of the external forces is equal to the mass times its acceleration. And the object itself is not kinematically moving. There might be an acceleration due to gravity, but because the object's not moving, it itself is not experiencing that acceleration. The acceleration manifests itself as a force. And so there has to be some other force that's equal to the force of gravity. And in the case of an object on a table, we're going to call that the force normal. And sometimes we can write it just as N for normal. And force normals always act in opposite directions of a surface. And so what we're having is the force normal is part of an equal and opposite pair that come across. The box is pushing down on the table. So the table has a force from the box. Force from the box. And that causes the table to move to the floor, and the floor pushes back up on the table. But that equal and opposite to this, the box on the table, or the box on the table has an opposite, which is the table back on the box. And that's the source of this normal, is the table back on the box. So let me see if I can point at things here, because I know my pointer stuff's a bit off. So plus I'm going to play with this, the fact that I can come over here and I can look at this. So right here we have my box, and the box is being pulled down by gravity, but the table holds it, and so the table pushes back up on the box. And so if we come over to my force diagram here, the box itself has two forces, gravity pulling it down and the table pushing it back up. If I were to explore the table itself more fully, the table has two forces on it. Well, it's actually going to have multiple. It has the force of the box pushing down on it. It has gravity pushing down on the table. And if I come down here and I find the legs of the table, which I don't have drawn, right, the floor is pushing up on the table. And so equal and opposite pairs manifest themselves in our force diagram. And so the thing we need to look on the box is we need the forces on the box only, which is gravity down and the table back up on the box. Now the Newtonian equal and opposite pairs that happen on this boundary, the box is pushing down on the table, so that's not on my force diagram. The box pushing down on the table is not on my force diagram because it's not what's happening to the box. But the table pushing back up on the box, which is the equal and opposite right here, that is my normal force. And anytime we have a surface interaction, anytime we have two surfaces together, no matter what their orientation is, the normal is perpendicular to the surface. In fact, the word normal mathematically will end up meaning perpendicular, or at a right angle to a surface. And so the normal force, or the normal in this nature, is the force of the table pushing back up on the box in this case. And so there's our equal and opposite pairs and how they manifest themselves in no motion. All right, let's look at another problem here. So let's say we have a canal. So I'm going to use some of my drawing tools here. Give me a second. Get some water going. Okay. So I have a canal. All right, a canal is a short little thing. I'll put some water in here. All right. And we have two people on either side of the canal pulling the barge. So I'll just put my canal boat in here. There's a canal boat. And so they have some type of tow rope connected to the boat. And they pull it so the boat's going in a straight line, straighter than the line I drew. And we can say that this is at a 45-degree angle to the straight line, and this is a 37-degree angle below the straight line. So we can look at the motion on this boat, and we can calculate, or we can have some way of measuring the force here. And so we're going to have a 40 Newton force here, and we're going to have a 30 Newton force here. And so we have these two forces coming across. And what we can look at is we can look at what motion that manifests in the boat. Now notice this boat and these directions start looking like something we've done before. They mimic our axes. So I'll come down here and I will make the boat on the origin. I want to make a force diagram here. But I'm going to make it such that it's going to focus on it as if it's a free body. Let's see, 40, is that 45? Yeah, I did 45. So I have a 45-degree angle up above, and down below I have a 37-degree angle. So that's like that. And notice how I've turned these into vectors. I've vectorized my quantity. So now I have a 45-degree angle, and the force in this direction has a magnitude, whoops, 2 seconds here. The force in this direction has a magnitude of 40 newtons, 40.0 newtons. And the force in the lower direction has a magnitude of 30 newtons. What color am I looking for here? Get my angle down here, and this is 37 degrees. And so we can talk about what motion we're going to see. We can talk about the force that the boat is experiencing. The boat is going to feel these two forces, and it's going to cause it to move. And if we think about it, it's going to move in this direction. It might have a little up and down direction to it, but it's definitely going to move down the canal. So we'll look at the components. So we'll talk about the forces in the x direction, so the sum of the forces in the x direction and the sum of the forces in the y direction. And so again, the vector lets us do these as components. Now both of these are positive in the x direction. Remember, first quadrant and fourth quadrant is positive. So I can think of, well, I'm going to call this force A and this force B. And so in my x direction, I have force A times the cosine of angle A plus force B times the cosine of angle B is going to equal the mass times the acceleration in the x direction. So I've taken my forces and I've turned Newton's law into something that will solve for one particular direction. So if we look at this, if we look at what we're getting here, is we have this force is going to have two components. It has a component that moves the boat in the forward direction, right? It's pulling the boat forward, right? Because that's what the two people are doing with the ropes. They're pulling. But their left and right, or the up and down on the canal direction, is canceling out, or at least being minimal. Right? You're pulling this tugboat, or you're pulling this canal boat, you want it to move down the canal. Sorry, the microphone gets really loud when I'm standing right here. Everywhere else it's really quiet. So if the volume gets a little, distorted, I apologize for that. And so these two ropes pull in a resulting force in the x direction. And our vectors, right, let us do that. I have the sum of the forces in the x direction, and then I'm going to have the sum of the forces in the y direction. So this vectorization that we did in motion is going to work. And notice all the way over at the end here, back here, where I'm off the screen, back where the MA is. A is a vectorized quantity. And so we can break these things back out into vectors. And from a problem standpoint, we can turn these into numbers. So I can have 40 newtons times the cosine of 45 degrees, because that's angle A and force A, plus 30 newtons times the cosine of 37 degrees is equal to the mass of the object times the acceleration in the x direction. Now, I haven't said how massive this boat is, so I can't tell you exactly how fast it's going, but we have the setup. We have our free body diagram, and we've got the components that will talk about the resulting force. And what this will sum out to is this middle part here will give me a sum of what's going on in the x direction. So if I take 40 newtons times the cosine of 45 degrees plus 30 newtons times the cosine of 37 degrees, I get 52 newtons, 52.2 newtons equals MA. And now I have the force that's happening in the x direction. And so that's how much of this work these two people are doing, or the energy they're expending, is causing a force in the x direction. And we can do the same thing for the y. I have f of a is equal to the sine of theta a, plus f of b is equal to the sine of theta b. And that's going to be the mass times the acceleration in the y direction. But notice here, we can talk about this angle two different ways. We can talk about this as being a negative angle, or we can talk about the co-angle that comes all the way back here, the same terminal. I want to make it a negative 37 degrees, which means that this is going to subtract. This is going to have a downward force. So when I go f of a, whoops, let me actually put in the value of f of a, because it's still 40 newtons, 40.0 newtons, times the sine of 45 degrees, plus 30 newtons times the sine of negative 37 degrees. It's going to equal the mass times the acceleration in y. And so I come back on my calculator, and notice the parallelism in this. Let me put this on the calculator, and then I'll point out the parallels. Plus 30 sine. Now I'm putting the negative 37 in, and this is going to give me 10.2 newtons in the y direction. So the boat's going to mainly move this way, but it has a positive y direction. So when we're done, the resultant force is a little bit in this direction. So the boat's going to tip a bit. All right. But let's look at this here. So I'm going to go back so I can point some things out, some parallelisms that are important in how these things work. So one of the things that we want to notice is when we did our quadrants for our angles, and we worked our way across with the different angles, in the first and the fourth quadrant, cosines were positive. And in the first and the second quadrant, sines were positive. So if I keep track of my sine like I did over here, I have to point back this way as I work my way out, then it's going to take the negative aspect of that. Now I could have made that a positive 37, But in doing that, then I would have to over here put a negative sign. Oh, wait, did it do it? Right here. That should be negative. So if I make that a positive 37 degrees, I have to make that a negative because I'm keeping track of my direction. Or I can use good reference angles, and the reference angle I'm using here is negative 37. The other thing to do is we could use the full 360, right? I come up and I come over and back and I do a full 360 here. I can use that full 360 to make this work. So we will let our angles keep track of our vector components for us, especially with forces. Alright, I'm going to plop this video up and then I'm going to move on to the next one. I'm going to do these in little chunks and we'll start working on some problems with how we do the sum of forces.